Welcome to a lecture on dimension. Today we're going to define the dimension of a vector space and then work on finding the dimensions of null A and col A, and then do a couple of dimension theorems. Here's the definition of dimension. If a vector space is spanned by a finite set, the dimension is the number of vectors in any basis of V. Now, that definition makes sense because of this fact. If a vector space has a basis of n vectors, then every basis has n vectors. So no matter what basis you use, there'll be n vectors in it. So that makes the definition well defined. If there is no basis for the zero vector space, so by definition we just say that has dimension 0, and then there's certain vector spaces that aren't spanned by a finite set. In that case, we say they're infinite dimensional, and we'll see an example in a second. All right, let's look at some familiar vector spaces and their dimensions. The dimension of Rn is n, because a standard basis, this happens to be the standard basis, but you could use any basis, is E1 through En. So for example, the dimension of R2 is 2, since a basis for R2 is 1, 0, 0, 1. Okay, the dimension of Pn. Pn is polynomials of degree less than or equal to n. This has dimension n plus 1. The standard basis for this space is 1t squared up to t to the nth power, and that's n plus 1 polynomials. Dimension of M22, that's a set of 2 by 2 matrices, is 4, and there's your standard basis. It's got 4 vectors in it. The dimension of the space of all polynomials is infinity, because you can't span the space of all polynomials with a finite set. And I put a little proof at the very end of these lecture notes if you're interested in seeing that. All right, so let's do some examples. Find a basis for, comma, and the dimension of, comma, the subspace W that looks like vectors of the form that I have here. And so that's going to be a subspace of R4. All right, and our strategy is going to be to find 4 vectors such that W is the span of those 4 vectors, put those vectors into a matrix, and find a basis for col A, because col A is the span of the columns of A. So I've already started us off. I took the given vector and separated it out into its A vector, its B vector, its C vector, and its D vector. And so this would be my V1, V2, V3, and V4. And if I put those vectors in as the columns of a matrix and call it A, then what I want is a basis for col A. Because in this case, col A is exactly the space W that we're talking about. All right, to make this lecture not so long, there's only a couple steps you have to fill in, but you should come up with this matrix here. All right, and you don't have to go to reduced echelon, you're just looking for pivots. So pivot, 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 columns 1, 2, and 4 of the reduced matrix have pivots, so a basis for col A is, remember, you have to go back and take the original columns from A, not from the reduced matrix. So a basis for col A is 1, 0, 0, 0, the first column. The second column, 1, 0, 1, negative 3. And the fourth column, 0, 1, 1, 1. All right, and that space call A, which remember, call A is W. Dimension W is 3 because we found a basis for W that had 3 elements in it. All right, let's do one with some polynomials. This will remind us, this will give us a review of what we did last time, finding coordinate vectors for polynomials. So here I've got 3 polynomials, and we want to find a basis for and the dimension of the subspace spanned by those 3 polynomials. So we're going to transform this problem to one in R3 by looking at the coordinate vectors. So remember, to find the coordinate vector of a polynomial, you just put in the coefficients. So the polynomial 1 is 1 times 1 and then 0, I'm using x's here, 0x, 0x squared. Polynomial, the coordinate vector for the second polynomial is 1, 2, negative 1. And the coordinate vector for the third polynomial is negative 1, negative 2, 1. So we put those in to a matrix A, and what we want is a basis for call A. It's always good to determine what you want. So that's what we want, and you can fill that in. I went ahead and reduced A for us. It didn't take long, but there's 2 pivots, columns 1 and 2. So a basis for call A is, I need to take the columns from the original matrix, 1, 0, 0, 1, 2, negative 1. All right. But let's go back and read the problem. Find a basis for the subspace H spanned by those 3 polynomials. So I want to give my answer not as vectors in R3. I want to give my answer in terms of polynomials. So a basis for H is, I want the first polynomial, 1, and I want the second polynomial, which is 1 plus 2x minus x squared. And the dimension of H is 2, because my basis had 2 elements in it. And remember, resist the temptation to just write call A is this set, or H is this set, because that's not correct. That's a basis for call A. Call A is spanned by those vectors, but call A isn't just 2 vectors. Those vectors form a basis for call A. So don't be lazy is what I'm saying. Okay. Let's do a couple more. Find the dimension of the subspace H that looks like the vectors ABC such that A minus C equals 0. Now, there's an equation in this description, so rather than using call A, we want to use null A. So we want a basis for null A, where A is the coefficient matrix 1, 0, negative 1. Because in this case, by definition, H is null A. Null A is the set of vectors that gets set to 0 by that matrix. So we're going to augment A with 0 and reduce. Of course, there'll be nothing to reduce. 1, 0, negative 1, augmented with 0. All right, so there's 3 variables. X3 is free, we'll call it T. X2 is free, let's call it S. And X1 is T. So my solutions look like X bar equal T times 1, 0, 1 plus S times 0, 1, 0. So a basis for null A null A is those two vectors, 1, 0, 1, 0, 1, 0. And the dimension of H is 2, because there's two vectors in that basis. All right, I suggest you pause the video for a second and try and do problem 4. All right, assuming that you paused and we're back, hopefully this is the way you handled it. You said, let A equal 1, 2, -4, -8, 2, -1, and you wrote down want a basis for col A. Col A is the space spanned by the columns of A. Well, that's exactly what we want. H is the space spanned by those three vectors. So col A in this case is H. They're one and the same. All right, so this shouldn't take long. One reduction will give us 1, -4, 2, 0, let's see, multiply by -2 and add 0. Hang on, beeper going. Okay, I'm back. 0, 0, -5. Pivot, pivot. So a basis for H, which is col A, is, we want the first two columns of A. 1, 2, sorry, the first and the third, and 2, -1. And the dimension of H is 2. All right, so one more topic, and then I'm going to stop the video and start up again with a second part. Dimension of null A and col A. This is the topic of the whole next section. It's called the rank plus nullity theorem, but I just wanted to give you a preview. If you have an M by N matrix, dimension of null A is the number of blank variables in AX equals 0. Well, let's go back to this example here. Every time you have a free variable, like an S or a T, you're going to get a vector that goes into the basis for the null space. So the answer there is free. Dimension col A, well, we get vectors in col A by looking at pivot columns. So this is the number of leading variables in AX equals 0. Well, the number of variables is n, because each column corresponds to a variable, and there are n columns. So the rank plus nullity theorem that we'll see next time simply says that this number plus this number has to equal n. The number of free variables plus the number of leading variables has to equal the number of variables. Makes good sense. All right, so here's a super quick example. Find dimension of null A and dimension of col A. This matrix is already in echelon form. So for col A, we just look at pivots. 1, 2, 3, 4. There's 4 pivot columns. So dim col A is 4. All right, there's 2 columns that have no pivots, so those correspond to free variables. So dim null A is 2. 4 plus 2 is 6, which is the number of columns. And that's it. So take a rest, try and do this problem on your own, and I will finish it when we get back on the next lecture, the next video, and I'll also do the true false with you. And then you've got some practice problems for home that have solutions written in.